You think calculus is boring. Derivatives, integrals, formulas you memorize to pass a test. But strip away the textbook and you find a mind trying to capture motion itself. A 22-year-old hiding from plague in a farmhouse, scribbling equations that will rewrite physics. No professor, no lab. Just Isaac Newton, alone with curves that refuse to stay still. What mental leap did he make that summer? What did he see that everyone before him missed? And why does it matter that you understand the exact moment reality clicked for him? Bubonic plague sweeps London, black spots on chests, bodies in carts. On July 25th, a boy named John Morley dies in Cambridge. First confirmed case, Trinity College empties, students scatter. Among them, Isaac Newton, 22, heads north 60 miles to Woolsthorpe Manor, his mother's farm in Lincolnshire. Isolation, 60 acres, sheep, orchards, a stone house with small windows. No one expects genius here. How do you measure something that will not stop moving? A planet sweeping across the sky, a ball arcing through air, the tangent to a curve at a single point. Every mathematician knows curves, circles, parabolas, hyperbolas. You can draw them. But touch any point on a curve and ask what angle the line makes there, right there, not an inch away, and the tools break. Euclid gives you static shapes. Algebra gives you equations. Neither gives you the instant. You draw a sextant line through 2 points on the curve. You shrink the distance between them. Fermat did this. Descartes did this. But infinity lurks. How small is small enough? When does close enough become exact? No one has an answer that works every time. Newton reads John Wallis, Arithmetica Infinitorum, published 1655. Wallis uses patterns. He finds areas under curves by summing rectangles, narrower and narrower, infinite in number. Wallis writes formulas for exponents. Newton sees the rhythm. He extends it. By early 1665, before the plague closes Cambridge, Newton discovers something no one else has. He finds a way to expand any binomial with a fractional exponent into an infinite series. Not just whole numbers, fractions, negatives, any real number. Write 1 plus x raised to the power n. For whole numbers, Pascal's triangle gives you coefficients. Newton pushes past. He writes 1 plus n times x plus n times the quantity n minus 1 divided by 2 factorial times x squared, plus n times the quantity n minus 1 times the quantity n minus 2 divided by 3 factorial times x cubed, on and on. If n equals 1/2, the series never stops. If n equals -1, you get 1 minus x plus x squared minus x cubed. The pattern holds. Newton writes it down. Manuscript dated May 20, 1665. He has calculus by the throat. He just does not know it yet. Newton wants areas under curves. He wants to integrate, though that word does not exist yet. Take the curve, y equals the square root of 1 minus x squared. This is the unit circle. The area from 0 to x is a quarter circle when x equals 1. The area is pi over 4. But what if x is anything else? Newton applies his binomial series. He expands 1 minus x squared to the power negative 1/2. He gets 1 plus 1/2 times x squared plus 3/8 times x to the 4th plus 5/16 times x to the 6th. He integrates term by term. Area equals x plus x cubed over 6 plus 3 times x to the 5th over 40. He has turned geometry into algebra. He has turned the impossible into a sum. Also, comment from which city you're hearing this from. Also, this script is researched and factual, using sources from the Cambridge University Library's digital archives of Newton's original manuscripts, MS Ad 4004 and MS Ad 3958, where you can see Newton's actual handwriting from 1665 and 1666, plus the 8-volume mathematical papers of Isaac Newton edited by D. T. Whiteside, published by Cambridge University Press between 1967 and 1981, which includes full transcriptions, translations from Latin, and scholarly commentary line by line on every calculation Newton made. These are not popular summaries. These are the primary documents. Now back to the information. How do you find its angle when you only have one location to work with? Newton thinks about motion. A point moves along a curve. As time flows, the point's position changes. The curve is not a static drawing anymore. It is a path traced by movement. The word comes from the Latin fluere, to flow. Position is a fluent. It flows with time. The rate at which it flows, that is what Newton needs. He calls this rate a fluxion. A fluxion is not an average speed between two moments. It is the speed right now, this instant. The instantaneous rate of change. If y equals x cubed, the fluxion of y equals 3x squared times the fluxion of x. In modern notation, di over dt equals 3x squared times dx over dt. Newton uses dots. A dot over a letter means fluxion. Y with a dot is the fluxion of y. Find the tangent at that point. The slope of the tangent is the ratio of fluxions. Newton can compute this for any curve you give him. He works through parabolas, hyperbolas, curves defined by polynomial equations, curves defined by his new infinite series. Everyone yields. The method uses infinitesimals. Newton imagines an infinitely small increment of time. Call it O, the letter, not the number 0. In that tiny interval, the fluent changes by an infinitely small amount. You form a ratio, change in y over change in x, then you let O vanish. When O disappears, you are left with the fluxion. But what is O? If it is 0, you divide by 0, which is nonsense. If it is not 0, you cannot let it vanish. Philosophers will attack this later. George Berkeley, 1734, calls them ghosts of departed quantities. Newton knows the logic is shaky. He finds a workaround. Newton writes this clearly in the second edition of the Principia, 1713. No more vanishing au reshaped, just a ratio that settles toward a definite value as the interval shrinks. This is the modern concept of a limit, though Newton does not use that word. He is inventing the vocabulary as he goes. If you differentiate and then integrate, you return to where you started. This is the fundamental theorem of calculus. Newton sees it before anyone. He writes it in his papers. He does not publish. His teacher Isaac Barrow circulates some of Newton's results to John Collins in 1669. A manuscript called De Analysi per Equationis Numero Terminorum Infinitus, written 1669, describes the method. Barrow sends it. Collins reads it. Collins is stunned. He writes back saying the author has extraordinary genius. But the manuscript does not print. Newton does not want it printed. He is 26, Lucasian professor of mathematics at Cambridge. He could claim priority. He does not. Meanwhile, in Germany, Gottfried Wilhelm Leibniz is finding his own path. Leibniz starts later. By 1673, he is studying mathematics seriously. In Paris, he meets Christian Huygens. Huygens pushes him toward deeper problems. By October 29, 1675, Leibniz writes down the notation we use today, the integral sign. The dx notation he publishes in 1684, Acta Eruditorum, a paper called Nova Methodus pro maximis et minimis, new method for maxima and minima. It is the first printed exposition of differential calculus. Leibniz gets credit in Europe. Newton fumes. He describes how he reached the calculus. He encodes part of it in an anagram. 6AC, CD, A13, EFF, 7I3, L9, N4, O4Q, RR4, S8T, 12VX. Unscrambled, it says in Latin, given an equation involving any number of flowing quantities, find the fluxions, and vice versa. Leibniz reads the letters. He is polite. He does not steal. He has his own methods. Different notation, different philosophy. Newton sees change as motion through time. Leibniz sees change as differences along a sequence of infinitely close values. Both work. Both are correct. But the priority fight will rage for decades. He does not publish it. It circulates in manuscript among friends at Cambridge. It finally prints in 1736, 9 years after Newton dies. By then, Leibniz's notation dominates. The world uses d and integral signs, not dots and fluxions. History gives both men credit now. But in Newton's lifetime, the battle is bitter. He will publish that in 1672, but he also keeps thinking about motion and force. Stuckley visits Newton in 1726, the year Newton dies. They drink tea under apple trees in the garden. Newton tells the story. He says he was in the same situation back then. The notion of gravitation came into his mind. An apple falls. Newton asks why. Why does it fall perpendicular to the ground? Why not sideways? Why not up? There must be a drawing power in matter. The earth draws the apple. The sum of that power must be at the earth's center. The moon is far away, but distance might just weaken the force. Newton imagines the force diminishes with distance. How? He guesses inverse square. Double the distance, quarter the force. This matches Kepler's third law for planetary orbits. Kepler said the square of the orbital period is proportional to the cube of the distance from the sun. Newton derives an inverse square force from that. Richard Norwood measured it between 1633 and 1635. He got 69.5 miles per degree. Newton does not have access to Norwood's number yet. He uses 60. His calculation does not match. The moon's orbit does not fit. Newton thinks maybe there's another force mixed in. A vortex, like Descartes proposed. He puts the problem aside. He connects the fall to the moon's motion. He realizes both are the same phenomenon. Gravity, universal. The same force that pulls the apple pulls the moon, pulls the planets, pulls everything with mass. This is the conceptual leap, not the math yet, the idea. Newton teaches at Cambridge. He argues about light with Robert Hooke. Hooke is prickly. He claims Newton stole ideas. Newton retreats. He hates controversy. In 1684, Edmund Halley visits. Halley asks Newton a question. If the force between the sun and a planet follows an inverse square law, what shape is the orbit? Newton answers immediately. An ellipse. Halley is shocked. How do you know? Newton says he calculated it years ago. Halley begs him to write it out. Newton agrees. He writes Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, published 1687. 3 books. The first lays out the laws of motion. Every object continues in uniform motion unless acted upon by a force. Force equals mass times acceleration. For every action, there's an equal and opposite reaction. These are Newton's 3 laws. They are foundational. They describe everything that moves. He does not reveal the fluxions directly. He translates everything into the language of limits and ratios. Lemma 1 in section 1 of book 1. Quantities that continually converge to equality become ultimately equal. This is limits, this is calculus. But Newton hides the machinery. Book 2 demolishes Descartes' vortex theory. Newton shows that a fluid vortex cannot sustain planetary motion. Book 3 applies the laws to the solar system. Newton explains the moon's orbit, the tides, the precession of the equinoxes, the orbits of comets. Everything fits. Universal gravitation. Every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. One law, all of nature. Joseph Louis Lagrange, a French mathematician, says Newton was the greatest genius who ever lived. He adds that Newton was also the most fortunate because you can only discover the system of the world once. Someone else will find relativity. Someone else will find quantum mechanics. But Newton found the universe first. Without integration, he cannot prove that a sphere of mass acts as if all its mass is concentrated at the center. This is essential. Without it, the inverse square law does not work for spherical bodies like the Earth or Sun. Newton spends months on this proof. He uses calculus in disguise. He gets the result. The math fits the cosmos. For him, curves are not static lines on paper. They are trajectories generated by moving objects. Time is the variable. Everything flows. As time advances, x and y change. The rates of change are the fluxions. X dot, y dot. These are velocities. Velocity in the x direction, velocity in the y direction. If you know the fluents, you can find the fluxions by differentiation. If you know the fluxions, you can find the fluents by integration. I dot over x dot. This is the derivative, di over dx. But Newton does not write it that way. He writes it as a ratio of 2 velocities, the velocity of y compared to the velocity of x. The tangent line is the curve at that instant. The slope tells you the direction of motion. If the slope is 2, then y is increasing twice as fast as x. If the slope is 0, y is not changing at all at that moment. The curve is flat there, a maximum or minimum. Find the maximum height of a projectile. Find the point where a planet is closest to the sun. Find the shape of a lens that focuses light perfectly. Each problem reduces to finding where a fluxion equals 0. Set the derivative to 0. Solve for the position. That is the answer. He also solves inverse problems. A ball is thrown upward. Gravity pulls it down. The acceleration is constant. Negative 32 feet per second squared. Acceleration is the fluxion of velocity. Velocity is the fluxion of position. Newton integrates once to get velocity. He integrates again to get position. He has the trajectory. He can predict where the ball lands. No one before Newton can do this with precision. After Newton, they calculate and forecast. The universe becomes mathematical, measurable, knowable. Equations, unknowns. Newton's mathematics is about change, flow, becoming. He takes the static world of Euclid and sets it in motion. He invents a language for describing processes, things that happen over time. Newton looks at a curve and sees a history. The curve is not just there. It was generated. Something moved to create it. A point traveled. A hand drew. A planet orbited. The curve is evidence of motion. The calculus is the tool for reading that evidence backward. Given the path, find the force that made it. Given the force, predict the path. He uses fluxions. He approximates the motion. He predicts the wobble. He matches observations. The math works. They prove the orbit is a parabola or an ellipse with extreme eccentricity. The comet is gravitationally bound to the sun. It will return. Halley predicts it will return in 1758. It does. Halley's comet, the first predicted return of a celestial object. Calculus makes it possible. Newton studies tides. The moon pulls the ocean. But why 2 high tides per day? Why not 1? Newton uses calculus to show the tidal force depends on the gradient of the gravitational field. The side of the Earth closest to the moon feels stronger pull than the center. The far side feels weaker pull. This creates 2 bulges, one toward the moon, one away. As the Earth rotates, coastlines pass through both bulges. 2 high tides. Newton explains this in Book 3 of the Principia. It is the first correct theory of tides. Newton uses calculus to compute the centrifugal force from the Earth's rotation. The equator spins faster than the poles. The centrifugal force at the equator is greater. This makes the Earth bulge at the equator. It is an oblate spheroid, flattened at the poles. Newton calculates the amount of flattening. Expeditions in the 1730s confirm it. The Earth is exactly the shape Newton predicted. It gives you the tools to not just observe the universe, but to interrogate it, to demand answers and get them. Calculations running down the page. He makes mistakes. He backtracks. He finds a better method. The surviving papers show this. Cambridge University Library holds them. MS Ad 4004. The waste book. Pages filled with early attempts. You can see him learning. He starts with specific problems. Find the area under this curve. Find the tangent to that curve. He solves each one individually. Then he looks for patterns. He abstracts. He finds a general method. He writes rules. If you have a sum, differentiate term by term. If you have a product, use the product rule. If you have a quotient, use the quotient rule. If you have a composition, use the chain rule. Newton discovers all of these. He does not call them by modern names, but he has the principles. He applies them to every problem he can think of. Circles, ellipses, hyperbolas, spirals, cycloids. Each curve yields its secrets. Newton compiles a list. In a manuscript dated October 1666, he solves 12 problems using his method of fluxions. Find the tangent to any curve. Find the radius of curvature. Find the area. Find the center of mass. Find the volume of a solid of revolution. Each problem is a demonstration of power. For parabolas, the area formula matches Archimedes. For ellipses, the calculations agree with Kepler's observations. Newton gains confidence. The method works. It is universal. It is calculus. Some differential equations have no closed form solution. Newton recognizes this early. He uses approximations. He expands functions into infinite series. He truncates after a few terms. He gets numerical answers. This is pragmatic. Newton is not a purist. He wants results. If you value documented history and rigorous mathematical foundations like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. Also, this script is researched and factual, using the Stanford Encyclopedia of Philosophy's entry on Isaac Newton last updated December 2007, plus the European Physical Journal H article by Gennady Gorelick from January 12, 2024, analyzing how Newton could have moved from a falling apple thought experiment to universal gravity in 1666. These are peer-reviewed academic sources with full citations. Now back to the information. Water is wet. These are descriptions. Newton demands quantification. How fast does it fall? How much does it rise? How hot? How wet? And more why? What causes it? You differentiate to find the rate of change. The rate of change often reveals the cause. If a planet's speed changes, a force is acting. The change in speed is acceleration. Acceleration is the second derivative of position. Force equals mass times acceleration. From the orbit, you deduce the force. From the force, you deduce the law. Inverse square, gravity. Schrödinger uses it for quantum mechanics. Every major advance in physics follows Newton's template. Observe, quantify, differentiate, solve. Calculus is the engine. Cooling of objects, spread of disease. If a quantity varies with time, calculus applies. Newton knows this. He writes about cooling. Newton's law of cooling. The rate of temperature change is proportional to the temperature difference. This is a differential equation. Newton solves it. The solution is an exponential decay. Temperature drops exponentially toward ambient. You can measure the constant. You can predict when an object reaches a certain temperature. Practical, precise. Change is everywhere. Motion, growth, decay, oscillation, wave propagation, heat flow, chemical reactions. All of these involve rates. All of these yield to calculus. Newton sees this. He sees that he has found a master key, a tool that unlocks every door, a language that describes all processes. And yet he hides it. Why? Newton is secretive. He fears criticism. He fears theft. He fears being wrong. When Robert Hooke challenges his work on light, Newton retreats for years. He does not publish the Principia until Halley begs him. He does not publish the method of fluxions until after he is dead. This is tragic. If Newton had published in 1666, calculus would have spread decades earlier. Leibniz would not have needed to rediscover it. The priority dispute would never have happened, but Newton holds back. He keeps his cards hidden. Only his closest friends know what he has. Leibniz's approach, using infinitesimals directly, is easier to teach. By 1700, continental mathematicians, the Bernoulli brothers, L'Hopital, are publishing results using Leibniz's calculus. England lags. English mathematicians use Newton's fluxions. They are isolated. They do not collaborate with the continent. British mathematics stagnates for a century. Not until the early 1800s does England adopt Leibniz's notation and rejoin the European mathematical community. Newton's secrecy costs his own country decades. Newton's insight that motion can be captured with infinitesimal analysis, that curves are generated by points in motion, that rates and accumulations are inverses, these insights are permanent. They are the foundation. Leibniz's notation may dominate, but the concepts are Newton's. The fundamental theorem of calculus is Newton's theorem. He saw it first, he proved it first, he used it first to unlock the heavens. Few people understand it, but those who do recognize its importance. Halley writes a poem for the preface. Huygens, the greatest scientist in Europe before Newton, acknowledges Newton's superiority. Newton becomes famous. He's elected to Parliament in 1689. He moves to London in 1696. He becomes Warden of the Royal Mint, later Master. He reforms the currency. He prosecutes counterfeiters. He is efficient, ruthless even. He publishes a second edition of the Principia in 1713, a third in 1726. Each edition refines the arguments, adds new data, responds to critics, but the core remains. The three laws, universal gravitation, the mathematical framework, calculus. Newton is knighted in 1705. Sir Isaac Newton. He never marries. He has no children. He lives with his niece Catherine Barton in his later years. He works on theology. He writes over 1 million words on biblical prophecy and church history. He studies alchemy. He seeks the philosopher's stone. These projects seem strange now, but Newton does not separate science and religion. For him, studying nature is studying God's creation. Understanding the laws of motion is understanding God's mind. He's buried in Westminster Abbey. The funeral is a state event. Voltaire attends. Voltaire writes later that England honors a mathematician as other nations honor a king. Newton's tomb is in the nave. The inscription says, "Nature and nature's laws lay hid in night." God said, "Let Newton be," and all was light. Alexander Pope writes that. It captures the feeling. Before Newton, the universe was chaos. After Newton, it was order. Quantum mechanics replaces Newtonian mechanics at small scales. Newton's laws are approximations. They work at human scales, at moderate speeds, but they break down at extremes. Does this diminish Newton? No, because Newton's legacy is not his laws, it is his method. Newton showed that nature is mathematical, that you can write equations describing physical processes, that you can solve those equations and predict the future, that the universe follows rules, deterministic rules, knowable rules. This is the Newtonian worldview. It dominates for 3 centuries. It is only in the early 20th century that physicists begin to question it. Heisenberg's uncertainty principle, quantum indeterminacy. The universe is not clockwork after all, but even modern physics uses calculus. Quantum mechanics is differential equations. General relativity is differential geometry. The method survives even when the specific conclusions change. And more, if you could manipulate those numbers with rules, you could predict outcomes. This sounds obvious now. It was revolutionary then. Before Newton, mathematics was for merchants and astrologers. After Newton, mathematics was for natural philosophers, for scientists. It became the language of truth. Every time you solve a differential equation, you walk the path Newton cleared. He made it indispensable. When they do not match, he adjusts, he refines, he tries again. This is science, this is mathematics, this is Newton. Just a young man with pen and paper and an unquenchable need to understand. In that time, Newton lays the foundation for modern physics. He invents calculus. He begins the work on gravity. He discovers the nature of light, all in isolation, all in secret. What happens if you remove Newton from history? Someone else finds calculus eventually. Leibniz did, independently. But the Principia, universal gravitation, the 3 laws, these might take decades longer, or centuries. Newton accelerates history. He compresses the scientific revolution into a single lifetime. He gives humanity the tools to explore the cosmos. He used his position as president of the Royal Society to bias the priority investigation in his own favor. The Commercium Epistolicum, published 1712, was supposed to be an impartial report on who invented calculus. Newton wrote it himself. He included only evidence favoring himself. He edited Leibniz's letters. He manipulated the narrative. This is not noble. This is petty. He was brilliant and cruel, insightful and vindictive. He gave humanity the keys to the universe, and he hoarded credit like a miser. And in a farmhouse in the English countryside, a 22-year-old sees how to capture infinity in an equation. He sees how motion becomes geometry. He sees how change becomes law. He writes it down. He does not publish, but he knows. And because he knows, eventually the world knows. Newton's calculus is not just mathematics. It is a way of thinking. It teaches you to see the world as a process. Everything is flowing. Everything is changing. You cannot step into the same river twice. Heraclitus said that. Newton agrees. But Newton adds this. You can measure the flow. You can write an equation for the current. You can predict where the river goes next. That is calculus. That is Newton. Dated 1666. Newton's handwriting, calculations, diagrams, attempts at proofs. They show Newton struggling with gravity. He uses the wrong radius for the Earth, 60 miles per degree. His calculation does not fit the moon's orbit. He crosses it out. He tries a different approach. He abandons it. The papers show failure. They show uncertainty. But the numbers are wrong. So Newton waits. He learns more. He finds better data. Norwood's measurement, 69.5 miles per degree. He tries again, 1684, 18 years later. This time it works. The moon's orbit fits perfectly. Newton writes the Principia. The papers in the walls prove Newton's process was messy, non-linear, full of dead ends, but persistent, relentless. He had the insight in 1666. He did not have the precision. He waited until he did. Then he published. Then he changed the world. Vision plus patience, insight plus rigor. A leap of imagination grounded by calculation. Newton saw further because he stood on the shoulders of giants. He said that himself. But he also saw further because he looked harder, longer, with more focus. He turned motion into mathematics. He turned mathematics into truth. And you, reading this, calculating derivatives in school, integrating functions on a test, you are using his mind, his vision, his language. You are thinking Newton's thoughts. And whether you know it or not, you are seeing reality the way he taught us to see it. It's something knowable, measurable, governed by laws we can write and solve and understand. That is Newton's gift. That is his legacy. That is what he invented in a farmhouse during a plague. Every bridge you cross was designed using calculus, stress calculations, load distributions, the curve of the arch. Engineers integrate forces to ensure the structure stands. Every phone in your pocket runs on calculus, signal processing, data compression, the algorithms that predict your next word. Machine learning is optimization. Optimization is calculus, finding the minimum of a function, taking derivatives, adjusting parameters, how storms form. Meteorologists solve these equations numerically. They use Newton's methods. They predict tomorrow, next week, the path of a hurricane, all calculus. Radon transforms. You take measurements, you integrate, you get an image of internal organs, you detect tumors, you save lives. Calculus makes this possible. You compute thrust, you integrate velocity, you get position, you adjust course, you land precisely. The same method Newton used for comets now sends probes to the edge of the solar system. Traders use it to value derivatives, risk management, portfolio optimization. All of this uses calculus, the flow of money, the change in value over time. Rates, derivatives. Financial derivatives are named after mathematical derivatives because they measure how prices change. Biology uses calculus, population dynamics, predator-prey models, the Lotka-Volterra equations. These are differential equations describing how populations of species change over time. How many rabbits, how many foxes, how they interact. Epidemic models, how disease spreads, the SIR model. Susceptible, infected, recovered, the rates of transition, all calculus. This is how public health officials predicted COVID spread, how they estimated hospital capacity, how they decided on interventions. The rate depends on concentration. Concentration changes as the reaction proceeds. This is a differential equation. You solve it. You predict when the reaction completes. How much product forms. Chemical engineering, reactor design, all built on differential equations, on Newton's calculus. Physics is entirely calculus. Mechanics, electromagnetism, thermodynamics, quantum mechanics. Every branch uses differential equations. You cannot do modern physics without calculus. Einstein's field equations for general relativity are 10 coupled, nonlinear, partial differential equations. You need calculus just to write them down. You need advanced calculus to solve them. Black holes, gravitational waves, the expansion of the universe, all solutions to Einstein's equations, all descendants of Newton's method. Bezier curves, B-splines. These are defined using calculus, the smooth motion of a character in a movie, the realistic lighting in a video game, ray tracing, path tracing. These simulate light using integrals. You integrate over all possible light paths. You get photorealistic images. The beauty you see on screen is calculated. It is calculus making imagination visible. He showed that you can take a complex process and break it into infinitesimal pieces. Analyze each piece, sum them up, get the whole. This is integration. Or you can take a complex process and ask how it changes moment to moment. Find the rate. This is differentiation. These two operations, integration and differentiation, inverses of each other, fundamental theorem connecting them, this is the skeleton key. It opens every lock. It solves every problem involving change. He used it to revolutionize physics. He kept it secret for decades. And when it finally emerged, when the world finally learned what he had done, everything changed. Science accelerated, technology exploded, the modern world began. Because one young man during a plague year figured out how to think about motion, how to capture flow in symbols, how to make infinity computable. That is the mental process. That is the achievement. That is why Newton matters. And that is why calculus is not just another subject you study. It is the lens through which we see reality, the tool we use to shape it, the gift Newton gave us from a farmhouse in 1665. Motion is everywhere, and now you can read it